Hello learners, in this presentation various types of fluid flow have been discussed. So basically this is a topic which comes under fluid mechanics and fluid machines, uh, which is a subject uh, is being taught in 4th sem BTech. So various types of fluid flow are listed over here, and namely these are steady and unsteady flow, uniform and non-uniform flow, laminar and turbulent flow, compressible and incompressible flow, rotational and irrotational flow, 1, 2 and 3 dimensional flow, ideal and real fluid flow, and natural and forced flow. So let us discuss these types of fluid flow one by one. So first of all, steady and unsteady flow. So flow in which the fluid characteristics such as velocity, density, viscosity, pressure, etc. at a point do not change with the time. So our velocity is function of x, y, z and t. Then at a fixed point or position, say for x1, y1, z1, the change in velocity with respect to time is zero. It means velocity is also constant. But uh, in unsteady flow, fluid characteristics at a point change with time. So the change in velocity with respect to time, or dou v or dou t, is not equal to 0. Now the next type is uniform and non-uniform flow. So flow in which the velocity at a given time does not change with respect to a space. So for at a given time, say for after 3 seconds, velocity change in velocity with respect to space is 0, and which can be represented as dou v or dou s is equal to 0. Whereas in non-uniform flow, velocity at a given time changes with respect to space. So again, for a given time, dou v or dou s is not equal to 0. It means velocity is varying. In this diagram, we can also see that wherever the cross section of the pipe is constant, then the flow is uniform. But the region where the cross section of the pipe is varying, the flow is non-uniform. We can understand these two types of flow with more examples. A steady flow could be uniform flow as well as non-uniform flow. So, and at the same time, unsteady flow could be uniform flow and non-uniform flow. So first of all, if steady and uniform flow, then the discharge is fixed, and the diameter is also constant, right? So, and in steady and non-uniform flow, discharge is constant, but diameter is varying. So water flow through a river with a constant discharge is also a good example of such flow, as the span of river generally varies with distance and amount of water flow in river is constant. Now comes to unsteady and uniform flow, a flow through a pipeline of constant cross section with sudden change in fluid discharge or pressure. But in unsteady and non-uniform flow, pressure surges in a flow through a pipe of variable cross section. A practical example can be water flow in the network of canals during water release. The next type is laminar and turbulent flow. So, if particles moves in laminars, why laminars? Because fluid particles move along straight and parallel streamlines, and these streamlines are equispaced. So, the particles moves in laminars, and hence its name is laminar flow. Laminar flow is also known as streamline flow and viscous flow. Whereas in turbulent flow, particles move in a random fashion or zigzag way. Hence, this formation takes place, and that results in high energy loss. So now, how to find out whether the given flow is laminar or turbulent? And so here the Reynolds number will come into picture, and basically Reynolds number is a dimensionless number, which is a ratio of inertia force to viscous force. Uh, Reynolds number can be written as rho v d by mu, whereas rho is density of the fluid, v is the average velocity of the flow, d is the diameter of the pipe, mu is viscosity of the fluid. For flow through pipe, is if Reynolds number is calculated and if it comes less than 2000, then the flow is laminar. If it comes more than 4000, then the turbulent then this is turbulent flow. And if it comes in between 2000 to 4000, then this is a transient flow. In the diagram shown that at low velocity there is laminar flow, and if the velocity is increased, so at high velocity the laminar flow converts into turbulent flow. This is basically a pictorial representation of Reynolds experiment. Now, compressible and incompressible flow. So flow in which the density of the fluid is not constant, say for with the change in pressure and temperature, then this flow is known as compressible flow. Whereas in incompressible flow, the density of the fluid is constant with change in pressure and temperature. So in general, flow of liquids is to be considered as incompressible flow, say for flow of water, as density is constant while changing pressure, or there is not a significant change in the density. Whereas in flow of gases is to be considered as compressible flow because there is a significant change in density while changing pressure. Now the next type is rotational and irrotational flow. So flow in which the fluid particles while flowing along streamlines also rotate about their own axis is known as rotational flow. Whereas in irrotational flow, the fluid particles while flowing along streamlines do not rotate about their own axis. So in this picture we can see that in the boundary layer region, fluid particles are moving and also rotating about their own axis, but beyond the boundary layer region the fluid particles are just moving, they are not rotating with their own axis. Now one dimensional, two and three dimensional fluid flow. The term 1, 2 or 3 dimensional flow refers to the number of space coordinated required to describe a flow. It appears that any physical flow is generally 3 dimensional, but these are difficult to calculate and call for as much simplification as possible. This is achieved by ignoring changes to flow in any of the direction, thus reducing the complexity. It may be possible to reduce a three-dimensional problem to a say for two-dimensional or even one-dimensional problem. So say for let us take velocity as a function of x, y, z and time t, then this is three-dimensional flow. Now this three-dimensional flow can be reduced to two-dimensional flow. Say for there is no significant change in the velocity in z direction, then we can ignore the flow, the velocity measurement in z direction, and now the velocity is function of x, y and time t. Now further it can be simplified as one-dimensional flow, whereas velocity is function of x and time t. Now it is not function of y and z. In the given diagram, 1D flow, the fully developed laminar pipe flow is to be considered as 1D flow. So here the velocity is function of r only. The another diagram is showing converging duct flow, in which the velocity is function of x and y, and hence it is an example of 2D flow. Now the next one is ideal and real fluid flow. So flow in which viscosity of the fluid is not considered. Whereas in real flow, the viscosity of the fluid is considered. In reality, there is no fluid which is not having viscosity, but for simplifying the mathematical model of the flow, it is assumed to be ideal fluid flow, such as assumption for Bernoulli equation. Now the next is or the last one is natural and forced flow. So a flow in which fluid is flowing due to natural means, say for gravity force, buoyancy force. This type of flow is known as natural flow, whereas in forced flow, the fluid is flowing with the help of external means such as a pump, fan, blower, etc. So this is type of forced flow. So that's all about various types of fluid flows. Thank you for listening.